So, a suffix tree, let us say T sub T. So, the suffix tree depends on this text. Okay, it is a suffix tree for the text, has the following properties. Is a rooted tree, has n leaves. So, okay. So, now over some sigma plus, okay, some alphabet sigma, and some non-empty string over that alphabet, has n leaves, each labeled each child of a node other than leaves is labeled with some unique symbol So, we remember we created this special symbol called dollar for a technical reason, and so you have this rooted tree having n leaves, and each child of a node, each edge is labeled with either something from that alphabet or the dollar symbol, okay, but all unique. You can't have two children with the same child label. Okay, let me make that clear. Okay, and okay. Concatenation of all symbols in the path from root to a leaf labeled I gives the suffix ti plus 1 T. Okay, so all this looks very formal, but we had a pictorial representation of a suffix tree, and I've just made things a little more formalized here. Let's see an example. Say sigma is some ABC, and your text is let's say 1, 2, 3, 4. Then the suffix tree looks like this. So, I will have a so we will add a dummy symbol dollar at the end. So, it says B dollar with label 10. C and dot dot dot. Okay, you can fill this up. Okay, is it clear what's going on? Just take a minute to absorb how I constructed this tree. All I want is, I look at this, what does 7 mean? That look at the suffix starting at position 7, A, B, C, B dollar is what I have when I read the root to that leaf path A, B, C, B dollar. Okay, so that's all. I just want, one leaf for every suffix, but I'm sharing the label. So I don't want to create separate path for every leaf, but when they overlap on certain symbols, I just use the common edges and then branch off wherever I need to branch off. Okay, is that clear? So you can fill up and construct the suffix tree. It will have all these properties. The rooted tree has n leaves, right? There will be a leaf 7, 10, 8, 6, 9. There will be a leaf for every number between 1 and 10. And the branch, if you look at any node, the children will have one of the characters or the dollar symbol coming out of it. And if you concatenate all symbols from root to a leaf, you will have that suffix. Okay. And do you remember why we added this dollar symbol? Yeah, why did we need to add this? There was some reason we added this. Hmm? Yeah, exactly. Right. So if I did not add this, then where will I have this? How do I capture the suffix 10? Because it turns out that this suffix is also a prefix of some other suffix. So this suffix B, a suffix is something which starts from position and goes all the way to the end. Okay. So this suffix B also happens to be a prefix of some other suffix. That means that if I don't add this dollar symbol, then I will not have a leaf corresponding to that suffix. Okay, so that's why we have this. Now, searching in a suffix tree for a pattern is pretty easy. So I want to search for this pattern P in the text T. I construct this suffix tree, and then what do I want? How do I check? So let's say I want to know whether BCA is in this string. Okay, I want to check whether BCA is appearing in this string. Then I just go to the root of this suffix tree, follow the edge labeled B, and then there is an edge labeled C. There is no edge labeled A. So far, hopefully there will not be any edge labeled A after I fill up this suffix tree. So I stop and say the BCA is not there. Okay. If I want to search for, let's say, CAB, then I follow this CAB, and then yes, I have come here, and yes, the pattern exists. Okay, so searching for a pattern P, P exists in T if and only if P is a prefix of some suffix in T. Therefore, start from the root and traverse by matching one character at a time. Until either the pattern is found or there is no child at a node with the required label. So, how much time does it take to search for the pattern, ignoring the construction time for the suffix tree? Proportional to the length of the pattern. Okay. Depends on how you implement this, because if I have, I mean, assuming that I can index into my character directly in constant time, right. So, if I have for every node I store an array of pointers for one for every character, and I may even have an empty pointer, then I can just go and index into that particular. I am looking for a B, I go to the B link and see whether there is a child, follow through, and then everywhere I look for a particular thing. If I do not store it in an array, but then I may have to search through all the alphabets there, which might add a multiplicative factor of size of the alphabet. Okay. So, so time, I will write this as order m or m times sigma depending on implementation. Okay. This is to check for pattern. Now, if I want to find out all occurrences of the pattern, then what do I do? How do I find this?
Find the pattern, and then you will stop at one node.
Yeah.
Find the number of leaves under that subtree.
Yeah. So, all leaves at that subtree tell you the starting position of the pattern, right, because this is a prefix of so many of these suffixes. That means that you go to suffix number whatever. Let us look at an example here. Let us say I am looking for pattern AB. Okay. Then I will follow through this and AB. So, there is a suffix starting at 2. So, there will be a, because for this suffix there will be 2, and there is a suffix starting at 7. Is there any other AB? No. So, when I stop here, then I know that all the leaves, their positions are telling me where this occurrence of the pattern is. Okay. Now, but how much time does that take to find all occurrences? Yes, we have the information in the suffix tree, but how much time does it take? What do you do? Right, it gets into details of how we are going to implement this. We could do some sort of a BFS, DFS, or some such thing. Basically, I want to get to all the leaves of this tree. So, when I am here, I could just keep going to its children until I find a leaf, and then follow some sort of a depth first search. That means the amount of time is proportional to the number of nodes in this tree. That is what a DFS would take, right. So, it is in my interest to reduce the number of nodes in this tree overall. Okay. So, we looked at a couple of optimization last time. Let me recall. So, overall the problem with this suffix tree is the space it is going to occupy. So, in the worst case, how many nodes can there be? N square nodes can be there in this, because each suffix can pretty much create a new path. So, there are n suffixes, one of length 1, one of length 2, one of length 3, and so on. So, you could have So, what would be an example of suffix tree? Let us say I look at all characters are different, but there are only 3 characters here. Right. Let us say I look at a power n b c power n. Then my suffix tree will have c power n minus 1, c n power n minus 2, and so on, c. Then it will start b followed by c power n, right, b followed by, yeah, okay. Is this the correct example? And I will have a, b, c power n, then I will have a square, right, one more a, b, c power n. Yeah, I think this, for example, will work. Yeah, right. So a, b, c power 1, c power n will be one suffix. Another will be a square b c power n. Another would be a cubed b c power n, and so on. Right. This would be an example of a suffix, a text whose suffix tree will have order n square nodes. Yes. Okay. So first optimization, let us call this compact suffix tree. Ensure that no node has a single child. By I'm going to be writing informally, but you can figure out by compressing such paths. Okay. So now instead of having, see this, the CB, if this is not really distinguishing, which means that there is no other child coming out of any of these nodes, then I am going to compress this whole thing into one path and write this whole string there. Right, so all these nodes go away. Okay, so that's what I mean by take these such long paths and make them into one edge. But now you put, now it's no longer suffix tree the way I defined, because your edges are not labeled with a symbol of the alphabet, but a substring of the sigma star. Your edges will have some strings. Okay, so is that clear what this optimization is doing? I'm just taking all single child nodes and then compressing them into one big edge with this entire text appearing as a label of that edge. What do I achieve by this? That this tree has, except for the root, I mean root can have 2 children, but other than the leaves, every other node has at least 2 children. Okay, so if you look at it as a graph theoretic tree, then every node has degree either at least 3 or 1. Okay, there are no degree 2 nodes except for one, which could be the root. Okay, which means I asked you to verify this, that the total number of nodes is linear in the number of leaves. Okay. So total number of nodes is at most 2n. Because it's just this degree 2 nodes which are creating large number of nodes. If I ensure that every node is at least 2 children, then the total number of nodes is at most 2n. Did somebody verify you have a simple proof argument for this? Okay, let's even omit the fact that the root can have degree 2. So suppose every node except leaves has degree greater than or equal to 3. Right, that's what it is. Every node except the leaves has degree greater than or equal to 3. Then I claim the number of nodes is bounded by the number of leaves. Number of non-leaf nodes is bounded by the number of leaves. Okay, so let's verify this. Let L be the number of leaves and N be the rest. Right? No, let's not call N. Okay, NL. What do we know about L plus NL? That's equal to N. That's the total number of nodes. Okay, I want to bound the total number of nodes. Let's write something about the degree, sum of the degrees, right? Sum of the degrees. What do we know about the sum of the degrees of all vertices in this tree? 2 times the number of? Yeah, 2 times n minus 1, right? And but we also know the sum of the degrees is greater than or equal to L plus 3 NL, right? Because leaves have degree exactly 1 and others have degree greater than or equal to 3. Okay, so now you solve this, you will get whatever I wanted. So let me write L equal to n minus NL. So n plus 2NL is less than or equal to 2n minus 2. Okay, so this n goes away. So NL sorry, yeah. So L plus, I'm going to write L as n minus NL. So n plus 2NL is less than or equal to 2n minus 2. So 2NL is less than or equal to implies okay, I'm overloading the word n here because I also said n is the number of leaves. Okay, so let's write this as capital N. So number of non-leaves is at most total number of nodes by 2. And number of leaves is n, and so you can figure out from here that total number of nodes is at most 2 into number of leaves. Number of leaves is n, and this is saying that number of non-leaves cannot be too many. Okay, so overall you have at most 2 n nodes. Okay, so so this is the thing which we achieved by doing this compression. The total number of nodes is at most 2n, which means, for example, finding all occurrences of the pattern can be done after you come here. Then you just go and find all the leaves in time proportional to the length of the text. Actually, you can say something even stronger. So this, I mean, keep this thing generally that if I have a tree where non-leaves of degree at least 2, at least 3, then the number of non-leaves is bounded by the number of leaves. Okay, that's what we argued here. If you have a tree where the number of every non-leaf is degree at least 3, then the number of non-leaves is bounded by the number of leaves. Okay, so which is the case here as well. That, I mean, how much time I'm, so come back to this pattern matching question where I find this pattern, spend time proportional to order length of the pattern, then I want to output all occurrences of the patterns, all starting positions, right. Suppose there are some k different occurrences. Okay, there are k different occurrences. What does that mean? There are k different leaves in this subtree. Then how many nodes are here? 2k, that's what we argued. So the amount of time, it's not even order n, that's all I want to say. The time you spend to find all occurrences, accrued upper bound is order n because I am visiting all nodes of this tree, which is bounded by the total number of nodes. But you can say something tighter, and that is that the number of occurrences is k, then the time you spend is order k. Okay, so let me capture this. Hence, finding all occurrences of a pattern, because at this point you will start checking with the edge labels and so on. I don't care, right? You're not doing any comparisons. Once I find that pattern, it takes me to a node. From then onwards, my goal is to go to all the leaves. That's all. I'm not even going to check for edge labels and doing any comparison. I just go to all the edge labels, all the leaves. So finding all occurrences plus k in a sense, this is really tight and optimal in some sense is what I want you to see, because order m is something unavoidable, right? You are reading a pattern and checking for it in the text. Order k is also something unavoidable because you have to output some k different positions. K is the number of occurrences you have to output. Okay, so it could be non-optimal in the constants you are using, but otherwise it's just pretty tight. Okay, I'm just saying somewhat, this is not very precise because when I talk about optimality and so on, I have to mention the model of computation, but just want you to get the idea that this is, a very efficient computation. Okay. Okay. So then another nagging thing about this optimization is that, again, when it comes to implementation, how do I implement this? Well, every node has some array of edges, each one for each character, and the edges are now having either a symbol or a string. Okay, so that's not something which I want. It's not nice to implement. So the way we dealt with it is by saying, well, if you're going to have a string, this string is actually a substring of my original text. So instead of storing the string, because the string length could be completely arbitrary, we just store the starting and end point of this string in that text. That means I am just remembering two numbers. These are just two numbers uniformly for every edge. Okay, so that makes implementation easy. So replace edge labels by starting and end point in text of this label, which is a substring. Okay. Okay, so now you can find whether or not the pattern exists, as well as all occurrences of the pattern in pretty efficient time. Okay, order m plus k if k is the number of occurrences. Now I want to tell you more applications of suffix trees. In fact, there are a lot of improvements to even the space usage. There is one idea which says that I just don't bother about remembering the substring, but I just tell you the length of the substring. Okay, so I come to this node, and the edge label, let's say that label length, there are some 4 symbols. I just remember number 4. Okay, now when I am searching for a pattern, I follow through. When I come to this edge, it says 4. I skip 4 symbols. Okay, because I don't know what that string is. Of course, if I remembered the starting and end point, I can go to the text and make my comparison. Otherwise, I just skip that symbols, 4 symbols, and I keep going, and I reach a node where I have a perceived feeling that I have found the pattern. I can't really confirm, right, because I skipped some symbols. So how do I confirm? I go to a leaf node, right, and go and follow through now, because I know if the pattern is there, any one of the leaves, if I start from there and follow through that many symbols, I will get my pattern. So I can confirm at that point. Okay, so there are lots of modifications. The advantage of this is that I don't need to remember the starting and end point, two values at the node. I remember only one value, the length of the string. Okay, so there are lots of papers written on improving space for suffix trees. Okay, so it's been a very interesting sub area, and there are a lot of papers as early as in late 2000 and so on. Okay, so I won't get too much into the space improvements, but I'm going to tell you at least a couple of more applications of suffix trees. Okay. So searching for a pattern P in multiple texts. Okay, so T1, T2, T capital M. Okay, let me make one more remark about the construction time for suffix tree, because that's also important, right? When I'm trying to do string matching, my overall time for string matching is actually I first construct the suffix tree and then search for the pattern in that, follow through the tree, right? You don't bother too much about construction time because that's done only once and you're going to do a lot of pattern matches. It's like, you know, the way we constructed an automata for a pattern and then we ran text over it. But construction time is also important. I mean, it's not very hard to see that you can actually construct a suffix tree in n square time. I was trying to construct this suffix tree, right, by adding one suffix at a time, last suffix, and then I take the previous suffix, run through the text, find the longest common substring, and then from there I branch on. Pretty much that brute force algorithm will give you an n square time algorithm to compute this, not compact, but this suffix tree, but there are algorithms that can do it in n log n time. Okay, so I'll just make, that's another in all this, I am assuming that sigma is a fixed size. So, that constant will go somewhere in these big O, it absorbs all these constants. Okay. So, it is a fixed constant. Otherwise, there is a dependence on sigma somewhere. Okay. Okay, so let's say this is n1, n2, and n is the length of these texts. Then, if I am looking for this pattern P and look for all occurrences of this pattern P in all these texts, one brute force way of doing it is to just to do one at a time. Right? I take my text T1, so I will have n1 log n1 time to build a suffix tree on this character, this text, run my pattern which takes plus m and so on. Okay, so this would be one way of doing it. Okay, but there is a better way to do it in all one shot, in particular by taking time proportional to only 1 m, not capital N m here. You just spend 1 m time and you will be able to find all occurrences of, I mean, well, plus the number of occurrences, of course, right, as we said here. Yeah, yeah. How do you make it? Yeah. Yeah. So that's a good idea. So it says, he says that I have, let's say, well, there's one little problem with that. We'll deal with it, but as an idea, that's what we're going to do. So I have a text A B C, another text which is another text which is, and I have a pattern, let's say A B, and I want to check where all it's appearing in all these three texts. Then I can build suffix trees for each one separately and run my search algorithm. Or what he's saying is now concatenate this whole thing into one large text, okay, and build one big suffix tree for this. Now you run your pattern and you can check. Okay, there is one little problem. What is the problem?
End of this, what text is starting of the
Yeah, you could spuriously report some patterns which are not there, right? So, for example, if I am looking for a pattern CA, CA is not here, not here, not here, but when I concatenate, it spuriously appears, and you can
You can have multiple. You can do it on multiple texts itself, but on the same tree, you can form the same tree with all the suffixes, and the leaf nodes, you can mark each of the leaf nodes along with the index. You can mark it with the text number also.
Sure, that we will anyway do. Even here we go, but
So
if you have multiple different suffixes, so you are going to have on the same tree you are going to build all various suffixes.
And we can have pointers. Each of the leaves can denote the text number and the index inside the text.
Yeah, there is one simple way to deal with this, which is to create your dollar symbols, right? So, I will have a $1 here, $2 here, and $3 as new symbols added. It will appear anywhere in this text, right? Now I have one large text. Now I build this entire suffix tree, and at the leaves you do exactly what you say, because you will have, let us say, for this suffix yeah. So, suppose these are the 3 strings and I add this, then I will have so this suffix. So, now I am going to write this as 1, 2, 3, 4, 5, 6, 7, 8. So, whatever, each one is of 6 characters. So, that is 6 plus 1, 6 plus 1, 6 plus 1. So, when I read this suffix, in the leaf level, you are going to have a number which simply says starting at position whatever, right, 7, 12 or something like that. Instead of saying I am starting at position 12, I will say I am starting at position whatever 4 of the second string. Okay. So, this is it. So, you basically concatenate all this with some delimiters, construct this one big suffix tree. So, your overall running time will be like order summation ni log summation ni, because that is the length of the total text. And I said you can construct this suffix tree in order n log n time. So, after you construct this whole thing, now I read this pattern, it takes me to a node, and I go to all the leaves there, and these leaves will tell me where all this pattern is occurring. Okay. So, I spend time proportional to only 1 m plus some more to figure out all the occurrences. Okay. So, here is a one shot, all you do is just take your suffix tree, concatenate and do it, and plus m plus the number of occurrences. Okay, so doing it n times gives you this runtime. Instead, construct a suffix tree for T1 $1, T2 $2. You can do some optimization here to reduce the number of nodes. In particular, if you have, okay, I mean, I won't probably get into it. Okay, no, I'll just leave it at the high level. So you can concatenate them all. The thing is that you spend only time proportional to once for the pattern, and then look at all occurrences. You will be able to report all occurrences and all the strings where this pattern is appearing. give so let's call this generalized suffix tree. Okay, again I'm abusing some symbols here. Earlier I said T1, T2, Tn is my string, where each one was a character, but here each one is a full string. Okay, so the other application is finding longest common substring among strings So I've given some strings like this, right? 3 strings A B A A B C, A B B C B A, B B C A A B, and I want to find out when there is no pattern here to search. I'm looking for the longest substring that is occurring in all these texts. And these are actually having very important applications in DNA strings and in genome mapping, and so in some computational biology problems. So they are very important problems. And yeah, so imagine how would you solve this? I mean, I'm looking at a common substring between every pair of these. There are n such strings. Okay. So just imagine without suffix tree first, then you will understand the power of suffix trees, right? Just imagine without suffix trees. I mean, how brute force trying to compare not just between any one pair, you have multiple different pairs, and you are trying to find which is the longest common substring. Okay. Okay. Now that you have imagined without suffix trees, yeah. So what do you do with suffix tree? Suffix tree of all of it. Okay, and then
there will be nodes which have n dollar symbols.
There will be nodes with n dollar symbols. Okay.
Yeah. And the longest common substring will be from the root to any of these nodes. So just find the path. You can solve it, show the height from there.
Any of it or
longest.
the depth?
Height.
Yeah. Yeah.
Find the depth.
Yeah. Okay. So that's it. So conceptually, that's it. Once you have the suffix tree, so step 1, construct the generalized suffix tree. Okay, so this suffix tree has suffixes of all of these texts, and the leaves have pairs of symbols, right? The first symbol tells you which string, second symbol tells you which position in that string that suffix is appearing. So now I'm going to say for every node, compute the two things, right? We'll see how to compute it. Compute for every node x depth of x. What is depth of x? Hmm? Number of nodes, that's all. At each edge you have this substring, so add them all, right? So yeah, so it's basically length, okay, of, let's call this as path label of x. And what is this path label of x? String obtained concatenating all substrings in the root to x path. Right, so I have a particular node x. Each edge has some substring with a starting point and end point. So take that length and add them all. Whatever that is, that's the length of that this thing. And then I'm going to compute the second thing. We'll come back to how to do this later. Let's call this m of x is the set of string labels in the leaves of the subtree rooted at x. Okay, so it's actually contained in 1, 2 of 10. So I have the depth of x plus, I look at this subtree rooted at that x, look at the leaves here. These leaves have a pair of values here. First value refers to the string, second value refers to the starting point, right? I explained it something like this, a string and where starting position that string. So I look at this first thing which tells you the string, I just note down those values and note that, right? So what is m of x? Tell me what is m of x? I wrote down syntactically, semantic, what is the meaning of m of x? M of x is a collection of strings. Out of T1, T2, Tn, maybe my leaf will have 3, 7 and 23, let's say. So m of x is 3, 7, 23. What does that mean? This pattern representing my root to x string appears in these strings 3, 7 and 23. That is what it is, right? Because the leaves are telling me all the strings where this pattern is appearing. Right? So m of x is precisely all the strings in out of T1, T2, Tn, which are the strings where I am appearing. Who am I? I am the string from root to x. If you take from root to x, concatenate all the substrings there, that is a string. That string is appearing in these leaves, because that is exactly what m of x is, right. So now tell me, by using these two notions, what is my answer? The longest common substring. Output path label x, where x is that string with the maximum depth among all x for which m of x is equal to what? I am looking at the longest substring which is common to all the strings, right. So I look at my suffix tree, look at a node which is the longest depth because that's I am looking for a longest common substring, such that m of x is what? 1 to n, because this string should appear in everything. So m of x is 1 to up to n. Okay, I mean, I would like to demonstrate it on an example, but it's tedious. I would like you to work it out. All I am doing is computing the generalized suffix tree, which has leaves having 2 values, and I look at, for every node I compute these 2 values, what is its depth of the string up to that point, and what are all the strings for which this pattern is appearing, m of x. Then I find among all the m of x values, look at where m of x is which have 1, 2, 3 up to n. Then these are the substrings that are appearing everywhere. Among all of them, pick the one which has the highest depth. Okay. Now let's quickly see how much time the whole thing takes. Right? I have to. I haven't told you how to compute all of this. I just said compute. I haven't told you how to compute and how much time will it take. So let's see how it. And let's assume that summation length of Ti some small n. So this I already said you can do it in order n log n. So this is an assumption which we actually didn't prove, but you can do it in this much time. After I have done this, construct the suffix tree. This has how many nodes? Order n nodes. At most 2n nodes actually. So I can compute this easily by doing some sort of a pre-ordered traversal of the tree, right? I just start from the root, go to all its children, and then compute their depth, because I just take the edge length, put it there. And then go to all its children, take the edge length and add to whatever the edge length of that children, and so on. So in order n time, by doing a pre-ordered traversal of the tree, I can compute this depths. Let's see how to compute these. Okay. This I would actually compute it in a bottom-up fashion by doing a sort of a post-order traversal of the tree. Okay. So how would you do? Because all I just say is string labels in the leaves of the subtree rooted at me. That's all I care about, right? So at the leaves, it's easy because I just take that string label and that's it. That's the set. And I go to the node above. What do I do? Just do a union of all the sets of your children, right? Because your children are giving me. So if I am here, so I have my m of x computed going all the way up. Okay, so if you do this calculations, I would say this takes order n, because I am at here, I just look at my parent, whatever that value is, and add that h, and I'm in constant time for every node I can do it. And here for every node, the time I spend is the time proportion to the number of children, which could be as bad as size of sigma, because number of children at a node is there could be 1 for every character plus $1, right. So I look at all those and do a union of all of them. Okay. So I'm going to write this as order n. For each node, I do sigma is the number of children I look at, and then I take the sets and do a union of them. Okay, so there is some time spent on doing the union. Each could be of size at most sigma. So, some such time. No, not no, capital N, right? Each could be of set size, right? So I have this set could be of size at most n. This set could be of size at most n. So overall, I take these sets, collect them all, and do a union. So I'm saying that that computation is going to take this much time. So this is my overall time, and yeah, so there are some, okay. So is that clear? I mean, I'll work out the details. I'm not being very precise here, but once you have a generalized suffix tree, you know conceptually what you need to compute, and you can either do it in a bottom-up fashion or a top-down fashion, and compute these sets, and then plus now you go over all the nodes here. So that's order n, looking at your m values. Whenever you find the m equal to 1 to n, you just note down the depth of that node and keep checking whether you are getting something bigger and bigger as you go down, and output the one which is the largest depth with m of x equal to 1 to n. So there are variations which are again important in computational biology of this question. You can talk about largest common substring of length L. Suppose I am interested in this. So what do I do? I mean, you do the same. I mean, you have everything there. You have the depth values, you have the m values. So output the path label x. In fact, you may output a lot of them with the maximum depth, or instead where x is that string of length L. Okay. One more application, I would just define this notion. We will actually do the application tomorrow, and that is pairwise overlaps. So I give you two strings x and y. This notion is an important thing in again biology and various string matching. Okay, so what is the pairwise overlap? It's simply stated, it's the largest proper suffix okay, I can formally define it, so you know what a suffix and prefix is. So what do I mean by proper? Meaning it's not entire x. Okay. So if I can write x as some w t, but w is not epsilon, and y is t x, where x is not epsilon, then t is the overlap between x and y. So, there is the order which matters here. The largest such t is the overlap between x and y. Okay, so let's see some examples. If this is my x, then in this case BBC would be the that overlap between x and y. Just think about how would you compute this overlap. Okay, conceptually it's not a very difficult thing. How will you compute? Okay, so before that, yeah, okay. This is an important concept in the construction of the automaton for the pattern. Okay, we will maybe come to that as well. Let's see what is the okay. If x is equal to AB, then what's the overlap of x with x? This is the order matters here. What's the overlap of x with itself? AB, right? I mean, you are tempted to say this whole thing is an overlap, but I wanted this w and x to be, not epsilon. So, AB is the overlap of A with itself. So, the largest proper suffix which is also a proper prefix, that is the overlap. Okay. So, think about how would you compute this, how much time will it take? Brute force computation. So, this is of length n. How do you brute force computation? So, you are looking for, think of it as you are looking for a t, the largest such t, right. So, what would be your first choice for t? I will come to that. Brute force is what I said. Suffixes is next lecture. Yeah, what is the largest choice for t? N minus 1, right? I am going to try this. Is this proper suffix a prefix? So, I will start comparing and then I fail. Once I fail, then I am going to start comparing this and so on and so forth. So, I decrease, right, because my t I start with this and do a comparison, see whether these two strings are same. If not, I move.
Or you can reverse the second string and then start comparing from the wrong.
It still doesn't help. So, pretty much the brute force, how much time does it take? In square time. Okay. So, the question you will be interested in is given a bunch of strings, I want to find overlaps of every pair of them. Okay. So, if I have each of length n and there are t strings, then this is like t square into n square is what if I apply brute force, right. For every pair t choose 2 times n square, and we will see using suffix trees how we can improve this running time. Okay. So, suffix trees started off as a structure to just to do some simple pattern matching. They turned out to be very powerful in answering a lot of questions on the strings. Okay. Longest common substring, finding a pattern in multiple texts, finding overlaps between every pair of them, and so on. Okay. So, we will see this next time. This. Well, we did this, no? We took the pattern, pre-processed it as an automaton, and we ran each text over it. So, how much? Oh, it's a good exercise. Let's see if you do it that way, how much time will that take, right? So, if I take the pattern, so that's like order m sigma square or something to build the finite automata, and then we spend time proportional to n1 plus n2 plus. For each text is run on this automata. Okay, so this is good on the text length running time, whereas here you are trying to spend time proportional to the size of the pattern. So, what will happen is here you are not necessarily finding for a pattern in multiple texts. Typically in real applications you have lots of text and you want to test a lot of patterns, okay, and that is where the generalized suffix tree is good, because you do this only once and then you run this for every pattern. Okay. Sure, there are. I mean, brute force, right? I mean, for a pair of strings, you can find the longest common substring.
But that may not be the.
That may not be the optimal thing when you are trying to find a substring for all of them.
That may not be even the optimal case.
When you have multiple strings, yeah.
A subset or something, substring of the string for 2.
Yeah. So when you have only 2 strings where I want to find the longest common substring, that's easy. You don't need suffix trees. You can pretty much do some dynamic programming or something. But for multiple things, suffix trees are powerful. I mean, there will be other ways, but it's very elegant using suffix trees.